In this final video of the section, I'll establish these two properties of trees. That if a graph has no cycles and it has the right size, then it must be a tree. And if G is connected and has the right size, then G must be a tree. So first we'll work on theorem 3.17 here. So proof. So let G be a graph with no cycles and M equal to n minus 1. So I wanna show that it's connected. So claim G is connected. Assume it is not. Then G has components G1, G2, up through GK. Necessarily, since G has no cycles, G is a forest, and each of the components are trees. This is gonna be similar to the proof of the corollary I did in the last video. Let n sub I be the order of each component, G sub I, and M sub I the size. So since each component is a tree, M sub I is equal to n sub I minus 1. Hence, all right, let's compute the order then. N is equal to the sum of the n sub i's. Or rather, I want to compute the size. Yeah, that's what I want to do. So n minus 1 is equal to the sum of the m sub i's, I equals 1 to k. But this is equal to n minus k, as we saw in the last one. If we add up all the sizes, each one is n minus 1. N sub I minus 1, the sum of the n sub i's is n, and I get n minus k. So n minus 1 is equal to n minus k, so k is equal to 1. That is, G just had one component, and so it was connected. So G was actually connected. That contradicts our assumption that it wasn't connected, it had components, and so that proves the theorem. I guess I didn't really need a proof by contradiction here, but it works. All right. So another of this type is that if G is connected and M equals n minus 1, then G is a tree. What I need to show here, right, all I'm missing to satisfy the conditions of being a tree is that G needs to be acyclic. So suppose G is a connected graph of order n and size m equals n minus 1. And suppose G is not acyclic. So suppose G has a cycle. Then remove an edge from cycles until we remove all the cycles. Until we arrive at an acyclic graph. By the way, this process of removing edges in order to make a graph acyclic, this is a research topic that a couple people here at PFW worked on some number of years ago. It's called the decycling number of a graph. And it's a pretty interesting research topic, and it does have applications. at any rate, what have we done here? So we had a graph that had a cycle. It had m equals n minus 1. We removed at least one edge from the graph in order to make it acyclic, and so m is strictly less than n minus 1. So arrive at an acyclic graph G prime of size m prime, which is strictly less than n minus 1. And so, right, so that's, this would contradict one of the previous theorems. Let me grab that previous theorem, 3.13. Right, so I started with a graph of order m equals n minus 1. I arrived at a tree. I just removed cycles, preserving connectivity, or preserving the connectedness of the graph, and I have size less than n minus 1, so this contradicts theorem 3.13, and that proves it. So to sum up a lot of these properties, these last, two properties, these last two theorems we looked at, we get this one that just kind of sums them up. So 1 and 2 together, 1 and 2 together, is the definition of a tree, right? Connected and acyclic. 1 and 3 together, well, that's theorem that's connected and m equals n minus 1. That's theorem 3.18. And then 2 and 3 together, that's theorem 3.17. So any pair of these conditions guarantees that my graph is a tree, and this will be useful for recognizing a tree. Okay, that's it for this video, and that's it for the section. Hope you enjoyed it a little bit. I know I did. I'll see you next week.